is the review week, so let's take a little bit to just have a brief overview of PDEs. In general, a PDE is a problem in which you want to find a function u that goes from omega, a domain that is a subset of Rn, and this function u is scalar. The form of the PDE is, in the very big generality, you have a function of the coordinates, the first derivatives of u with respect to any direction, the second derivatives of u with respect to any couple of directions, and so forth up to nth order derivatives of u with respect to any couple of variables, and you set all of that equal to 0. When you look at the highest order derivative, then that is the order of the PDE. We haven't looked at general order PDEs. We have settled ourselves to look at second order PDEs. In general, a linear second order PDE has this form. You have a sum of aij, that could be anything, multiplied by the second derivatives of u with respect to any couple of variables, plus a sum of bi times u derived with respect to one variable, plus cu plus d equal to 0, where aij, bi, c, and d can be functions in general, or usually constants. And what we dealt with was only in the constant situation. Actually, we simplified even more. Most of the PDEs we have looked at are linear PDEs with only second order terms. So we don't have first order terms, we don't have zeroth order terms, and we don't have any forcing term. If you have something like that, so you can write it as a sum over I and j from 1 to n, where n is the dimension of the space omega is embedded in, aij u xi xj equal to 0. And you can always rewrite this as in this linearized, quadratic format, that is the inner product between the vector of derivatives with respect to all the constants times capital A multiplied by the vector of derivatives with respect to every constant, all of this operator applied to u equal to 0, where A is symmetric. Capital A could be a constant, could be a function. Either way, you're considering it to be a matrix, n by n matrix, that is symmetric. We looked at cases in which capital A is a constant, so we can study the eigenvalues of this capital A. And if we study the eigenvalues of this capital A, we can determine the type of equation we have. And we have been studying, studying 3 examples of the 3 types of equations that you can end up having. So you have 3 options for the eigenvalues. One of the eigenvalues is 0, at least one of the eigenvalues is 0, in which case you don't check any other eigenvalue, you know that the type is the parabolic equation, and you're thinking of it as the heat equation. The heat equation is the example of the parabolic type PDE. Otherwise, you can have all the eigenvalues having the same sign. It doesn't matter if they're positive or negative, they're all on the same side. That means that the type of PDE that you're looking at is elliptic, and you have the wave equation. And then sometimes you have eigenvalues that are positive and eigenvalues that are negative, but none being 0. Then you have hyperbolic type PDEs. The example we have seen is the Laplace equation.